Hi everyone, this is Mrs. G.A. and today we're going to talk about conditions for parallelograms. So before we start actually proving that a quadrilateral is a parallelogram, let's start with the basic definition of a parallelogram. So if both pairs of opposite sides of a quadrilateral are parallel, then the quadrilateral is a parallelogram. So there are 4 different ways that we can prove that a quadrilateral is a parallelogram other than showing that both pairs of opposite sides are parallel. And so the first one is if both pairs of opposite sides of a quadrilateral are congruent, then that's enough for us to conclude that the parallelogram is that the quadrilateral is a parallelogram. Again, that needs to be both pairs of opposite sides. So another way that you could prove that a quadrilateral is a parallelogram is if one pair of opposite sides is congruent and parallel. Then that's enough for us to state that the quadrilateral is a parallelogram. So again, we only need one pair, but it has to be both congruent and parallel. And again, that's enough to state that it is a parallelogram. Our third option is if both pairs of opposite angles are congruent, then that's enough to state that the quadrilateral is a parallelogram. Again, it needs to be both pairs of opposite angles. Or our last option is if we can determine that the diagonals of a quadrilateral bisect each other, then that's enough for us to state that the quadrilateral is a parallelogram. So keep in mind, as we go through these problems, we're going to be looking for ways to use one of these 4 theorems to prove that a quadrilateral is a parallelogram. Okay, so let's try this first one together. So here we're asked, is EFGH a parallelogram given that A is 4.3, so I see A right here, and B is 13. So if we can determine it, we're going to state the theorem, and if we can't, we're going to explain why not. So if you look at where the given information is, you see that it's within the diagonals, and so we know that if we can show that the diagonals of a quadrilateral bisect each other, then we could prove it's a parallelogram. So we're essentially asking ourselves the question, do the diagonals bisect each other? If the answer is yes, then it is a parallelogram. So the first diagonal I see, or the first one we can work with, is HF. So we're essentially going to first check, is HI congruent to IF? So I'm going to put a question mark by it because we are not sure. So again, that's the 2 segments of our diagonal. So we know that HI is 2A, and IF is 0.5B plus 1.1. So I'm going to substitute the values we were given. And we're going to see if this statement is true. So here we get 8.6, and on the other side we get 7.6. So we can see that in this case, HI is actually not congruent to IF. So we don't even need to check the other one because this one doesn't work. So we would say, no, this is not a parallelogram because the diagonals do not bisect each other. So remember, it does have to work for both diagonals. So it may be true that EI is equal to IG. We're not sure, we haven't checked it yet, but you do have to make sure it works for both. So since it does not work for this diagonal, we cannot state that this is a parallelogram. Okay, let's try example 2 together. So here we have a quadrilateral with the vertices 1, 1. So I'm going to plot these as we go. And that is E. 4, 5. That's F. And then we have G is at 6, 6. And then we have H is at 3, 2. So this is F, G, and H. Okay, so we've plotted E, F, G, H, and now we're going to use the Pythagorean theorem to find the length of EF and to find the length of GH, because this is one way we can start checking to see if this is a parallelogram. So remember, for the Pythagorean theorem, we're going to turn this into a right triangle, and then our hypotenuse is EF. So I see that my height here is 4, and then I'm going 3 this way. So remember, the Pythagorean theorem is a squared plus b squared equals c squared. So here we have 4 squared plus 3 squared equals c squared. So we have 16 plus 9 equals c squared. 25 equals c squared, and if you square root both sides, we get a length of 5. So EF is equal to 5. And then we could do the same for GH. So again, I have a length of 3 and a length of 4, so it's actually the same right triangle, so we get the same length of 5. And we could set up the same exact equation to get that same answer. So we can conclude that EF is congruent to GH. So the next thing that we are going to need to check to see if they are parallel. And we could see if they're parallel by checking the slopes. So remember, for slope, we do rise over run. So the slope, I'm going to say M of EF is 4 over 3. And it is positive, so I'm going up 4 over 3. And then the slope of HG or GH. So again, from here I'm going up 4 over 3. So my slope is 4 over 3. So since the slopes are the same, we can conclude that those two segments are parallel. So they are parallel because they have the same slope. So we've now concluded two things. We know that the two segments are congruent, and we know that the two segments are parallel. And so that was one of the theorems that we learned on the last slide. So we do know that yes, EFGH is a parallelogram, and the reason why we know is because one pair of opposite sides is both congruent and parallel. So remember, if you can find that one pair is both congruent and parallel, we can state that it is a parallelogram. Okay, so let's try these last two together. So here we're going to determine if the quadrilateral is a parallelogram, and if we can determine that, then we are going to state the theorem that justifies it. So in this first example, I see that we have a diagonal, and I see that this angle is congruent to this, and this angle is congruent to this angle. So let's start by thinking about this problem as these two lines cut by a transversal. So if I look at it in this way, I see that these two angles are congruent, and we would call these two angles alternate interior angles. So remember, when your alternate interior angles are congruent, that means that these two lines must be parallel. So again, since I see that I have alternate interior angles that are congruent, that means that the two lines must be parallel. And then if I look at the same problem in terms of these two lines cut by this transversal, I see the same scenario. I have another pair of alternate interior angles that are congruent, which means that these two lines must be parallel as well. So since I have two pairs of parallel lines, we can conclude this is a parallelogram, and we can actually just say definition of parallelogram. Which again is two pairs of parallel lines. Okay, so let's look at this next one. Here, all I see is that I have one pair of parallel lines. So we don't know that these are parallel, and we don't know that these are congruent. So we cannot say, again, we don't know that line segment QU is congruent to line segment DA. That is not apparent to us. And then we also don't know that DQ is parallel to UA. So again, we don't know that these two are parallel. So in this case, there is not enough information for us to determine that it is a parallelogram. So we'll say no. Okay, so remember, we either need two pairs of parallel lines, or these need to be both parallel and congruent. All right, that is all for today's lesson. Thank you so much for watching.